Appreciate the opportunity to present tonight on some local research that's been done in Alaska, as well as give a little bit of a national overview of some products that are being used to try to create fuels on a non-petrol basis. Not that there aren't petroleum products used in some of the processing and some of the machinery, but at least for the inputs and the outcomes. So in ag country, biofuels were fairly popular about a decade or two ago, especially in the Midwest when there was a lot of talk of ethanol, of converting the BTUs in corn for consumption in cars and for having it as a liquid form for transportation. But tonight, I think you'll see that there are a number of uses for biofuels, that it isn't just in liquid form or a biodiesel, but there are also ways of using it for space heating. So I want us to start out tonight by saying that there will be basically 4 parts. One will be just kind of a general primer of biofuels in general. Then I'd like to take a look at some of the ag products that are grown, especially oil seeds for fuels, and then take a look at how biodiesel contributes, using some product and mixing it with diesel and running it in combustion engines, and then ways of using bio-waste, including fish and such, waste, to come up with solutions again for space heating for the most part. So, in general, biofuel is simply just a liquid that you can make that either will come from a plant, algae, or animal parts, animal fats. So the crop plant may be oil seeds, such as we'll discuss at first, or it may be vegetable oil. Algae I just came back from the International Biomass Conference in Minneapolis, and it probably isn't real feasible up in our area, though we have a lot of coastline and such, as much as it is in the warmer parts. They're doing a lot of work with it off the warmer coasts down south. And there are places even in the Midwest that are using algae, growing them in large ponds. But there's a different type of processing. They tend to throw it in with anaerobic digesters, which we'll talk about a little bit later. So animal waste, not just fish, as I mentioned, but even turkey poop's being used to drag the BTUs out of it for gasification of fuels, mostly for space heating. So some of your bio products can be pressed and immediately used in a traditional diesel combustion engine. Some are going to supply heat just in the form of burning the straight BTUs and pumping heat in for like space heating and such as that. And in some cases, the fuels can also be used to go ahead and drive turbines, water vapor turbines, and to get electricity from the use. So the applications of biofuels are pretty wide and broad: transportation, heating, in addition, like I say, even electricity. And so, as I mentioned, we'll see a little later that when you get a raw product, either from pressing seed or from vegetable oil, there may be advantages of mixing it somewhat with diesel, again, just depending on what your goal is. So in Alaska, there are 2 main types of biofuels that are, I guess, obtained from ag products. Obviously because of the short growing season and the incredible height that we have of sunlight, especially in the interior and Palmer, it's not real conducive to corn for ethanol, for instance. Now there is corn being grown as feed corn down on the Kenai, but you could never really make it profitable enough to try to raise corn. Your inputs and your energy would be too much on the Kenai to try to get the kind of scale that you would need to go with some type of ethanol production. But especially up in the Delta Junction area east of Fairbanks, they tend to grow a lot of barley, which isn't an oil seed, okay? But they can go ahead and also grow canola. And canola comes off, you'll see that's the canola flower up in the left-hand corner. And you can get rapeseed, which can be crushed, and then that seed secretes an oil. Another type of plant, and by the way, some of the farmers up in Delta just this year, for the first time, are making a real concerted effort towards securing land so that this planting season they're going to actually put some canola in the ground, or some canola in the ground, and see how it presses out in the end. But they're also using the camellia, and up in your right-hand corner is the seed, and that can be pressed too to get the oil. Generally, when you press these products, you're putting them in, I guess the best way to describe it is a huge fertilizer bin, and you're drawing them into a press that kind of looks like if your mom during Christmas made Spritz cookies, where she put the dough in and she cranked and pushed it through a screen. There's a round screen like that with holes about the size of pencil erasers, and it just extrudes the seeds right through there and kicks the meal. You get kind of what looks like a raw meal that's just ground up to one side, and then you have a channel that just allows this dark green brownish oil to flow into a large vat. And you can actually pour that straight into a diesel engine if the diesel engine has never been started up on diesel. All right, now a lot of farmers, what they'll do is they'll grow canola, okay, and it takes diesel as an input in their tractor usually to plant and to harvest, right? So they get on a cycle where they'll grow canola, they'll go ahead and they'll press it on their farm, and the School of Natural Resources and Agriculture at UAF has a press that they're going to try out this year, and it's kind of a mobile unit so that different farmers can try it under their own circumstances in the Delta area. And the canola, if they had diesel tractors before and ran diesel in it, they have real, well, not significant maybe just by the eye, but they have enough deposits from the diesel that the canola, when you run it straight through, it scours and cleans those deposits off, and then they get into your rings and your pistons, and then you've really got some problems. But if you take a fresh engine that hasn't been used yet and you run it straight through, then you don't have this problem of these dislodged deposits messing with your rings and your pistons, and you can run it straight off of there. Other plants, as I mentioned, algae, a lot of experimentation is being done, like down in wine country and such like that. They'll tend to go ahead and cut real large furrows or develop ditches to put stagnant water in, and they'll start to grow the algae, and they'll even put plumes of protective covering over them to keep the heat in and to get the algae to, I don't know if the right word would be germinate, but certainly to grow very thickly. Soybeans are used for the oil at different places, but not as favorably as far as engines and tractor engines as the canola. And then we're going to see a little later that even wood chips, 2-inch wood chips, you can gasify them. And we'll look at the process a little bit later with a portable machine that's gone commercial that you can even use at your home to produce electricity. You can gasify them, and you can then take the vapor from the gases of the burning wood, and you can condense it by cooling off some of that vapor and having it more or less poured off to the side and put it back into a liquid form. So one of the things that I want to emphasize that you might not normally think of is when we think of trees, we think of forestry. But the U.S. Department of Agriculture, as much as, well, I shouldn't say as much as, but it worked obviously with corn, all right, and Department of Energy on solutions of making ethanol. USDA is also very involved with wood, because in the industry codes that are used in North America, wood and trees are seen as a crop. They're actually seen and classified as an ag product. This is somewhat important when you're looking for grants and you're trying to find sources to try to figure out exactly how things are categorized, because you might be able to cross over if you had an experiment project that you wanted to do with even a couple of different agencies. You know, Department of Energy may be interested in. And as far as wood gasification, you know, it might be also that USDA is interested in. And even in some cases where they're starting to make biofuels for fighter jet fuel, Department of Defense will sometimes do investigative RFPs to try to get production because they have certain quotas that they're trying to meet as far as turning all of their fuels for their ships and their aircraft into biofuels. Not to supplant their whole petroleum regime, but at least part of it. So I mentioned that biofuels, in general, there's this ASTM 6751 standards, and it's generally accepted that on the newer engines, that if your biodiesel meets that requirement, or your biofuel, and you're probably mixing it with some diesel to get there, your engine should be fine. I mentioned, though, that this whole thing about running the seed oil straight, it needs to be a virgin engine. I also, rather than one that has deposits from diesel, if you have a diesel engine, like a Case or an International Harvester tractor or a John Deere tractor, there is a way. Andrew Soria, who's a researcher in this area at the Palmer, he kind of works out of the experimental farm station. He says that you can carefully titrate your mixtures so that you can, you know, start out with just a little bit of your pure canola, mix it with a good amount of diesel, and then your next round that goes through the engine, you go ahead, and I don't know whether it's half and half, but you slowly increase and wean yourself off the diesel. He says it takes about 3 different rounds to titrate and to finally get there, so that slowly those deposits are coming off. Now, vegetable oil is something that is used on engines that even might be a dual source. So the director of the Alaska Center for Energy and Power out of Fairbanks, which is kind of the research arm for the whole state, to look at different power sources, where they work, how they work, what's the best type of efficiencies out of them. On the back of her car, she has a little sticker that says powered by vegetable oil. And believe it or not, she has 2 tanks in the car. She has one that she runs vegetable oil on, and then she has one that has traditional petrol fuel. And I believe it's a switch within the car. She can switch tanks and still run it off the same engine. And I believe that she gets most of hers as WVO, waste vegetable oil, out of fryers in different restaurants. There have been experimentations, though, with just using straight vegetable oil also. So you can modify an engine, or like I say, you can have a car that uses the same engine for both. And so in some states, there's quite a bit of experimentation done with the 2 oils. In Alaska, you know, there probably just isn't enough critical mass of fast food restaurants and such to really do experimentation and spend the time and the money and the effort to see how those fluids operate in really cold conditions, or on the coast in really wet conditions and such, just because there won't be that much demand due to the lack of supply. Another thing that I should mention is that the economics comes in to the whole biofuel scene when you start to compare not so much the cost of what it takes to produce or press seeds and get the oil compared to diesel, okay? You may have a situation where it's maybe $3 a gallon, I'll be hypothetical, to go ahead and produce, and actually I think $3.96 is a reliable figure from what I've seen on a national basis, of taking canola, and when you figure all the costs and you press it, okay, $3.96 a gallon. Well, if you have 4 1/4 diesel fuel, it seems like, especially if you're going to use large quantities, it's a no-brainer to go ahead and use the canola, because you've basically got a cheaper product as an end after you figured all the production costs in. But in economics, we talk about opportunity costs, that just because something is more viable than one opportunity doesn't mean that that's your maximum efficiency of getting the most bang for your buck. And in this case, canola oil will probably, if we had the infrastructure to refine it, it probably wouldn't be used in tractors, because you'll find canola oil on the shelf, and albeit it needs to go through a little more processing in grocery stores and such. And in some parts of the nation, it's as high as $16 a gallon, from what I'm told from our seed fella at School of Agriculture and Natural Resources. So his comment is, yeah, it may be cheaper to use than the petrol, but why not go ahead and put it through another process at just a little bit more cost and get $16 a gallon for it and use it as food product. And my understanding is that there are opportunities also with using salmon oil, all right, from the processors here in Alaska. There's a lot of waste that goes out, a lot of oil that can be separated. But my understanding is that the health and the pharmaceutical value of the oil may very well trump what would just be kind of the base value to burn it for heat within the factory. So again, you kind of, in looking at this, you need to look just not in the energy vein, but what can that product be as a substitute good in a totally different market. And that'll, you know, indicate whether that industry is going to grow or not. So let's take just a little deeper look at oilseed production. Oilseed production, you basically have machinery, and it might be sunflower seeds, could be peanuts, all right, as well as I mentioned soybeans. You bring the product in as raw crop, and it's been separated from the leaves, or in the case of even corn, you've stripped it, and that's not an oil seed, but you've stripped it from a cob. But we're just talking about the kernel of the seed. And so you have a process that must go ahead and take care of not only making sure you just have the seed separated from the leaves and the twigs, but you also want to get any foreign matter out of there that maybe have been collected in harvest. And then your second stage is this crushing activity. And so there may be other ways of dealing with other types of seeds, but in general, like I say, canola being one of the more popular ones, all you're doing is just extruding the material out. And then you take the meal, and the meal may still have oil in it. So you've got the separating, then you've got the crushing. You separate the meal, and you may even use, as we'll see here in a moment, solvents to even eke out more oil out of the meal that didn't come out during the crushing process. But in fiscal terms, they talk about the crushing margin, and that just simply is a term that talks about the difference between the cost of the actual seed and then what you're getting out as the end product. And as I mentioned, you need to just be aware of other markets besides energy.
What percent recovery are you talking about?
As far as on your first crush, getting the oil out of the meal. So the figures, I'm shooting off the top of my head, and I can reference them pretty quickly, but the figures that I've seen are that you can get at least 2/3 of the oil on a single crush, 2/3 of the oil out of the seed.
So what's the percent by weight?
Well,
So
Yep.
feed, what do you end up with?
I'll show you in a moment.
Okay.
I'll show you in a moment. I've got some of those figures here. So as I mentioned, you can enter a solvent, and the solvent also, by the way, it not only is helping to in the process after you do the crushing in the separation, but it also can change the qualities of the oil, what kind of temperatures it takes until it starts to gel, things like that. So as I mentioned, it's kind of the step that you would use to kind of get that extra margin bang for your buck out. You'd asked here, typically used facilities with capacities of less. So it also comes down to sometimes the scale of the amount of material that you're working with as to whether you're going to invest in solvents. And this is out of the university, by the way, this slide out of the University of Montana. And they have quite a bit of open field that they collect quite a bit of canola out of.
Is there a universal solvent that they're using, like hexanes or?
You know, I think, yep, and I believe that it is a hexane, and I think my YDEs and all of that from chemistry I've totally forgotten, but I believe that you're working with a methylhexane, I believe. But I can look that up pretty easy and get it back to you. But there is one common solvent that's usually used in the industry.
Okay.
Yep.
It's not like, specific solvents.
My understanding is that there's just one that really tends to work, at least for canola. And so as I mentioned, the different scale will also kind of dictate as to whether it's worth your time to go through on the processing. So with solvents, you can get about 99% of the oil, but you want, and it's not an evaporation process, and it was explained to me just one time, but there's a way in which you enter the solvent, you get everything you can out of it, and then you exit the solvent as thoroughly as you can out of the oil for the sake of the rubber seals and stuff like that in the engines if you're using it for combustion. And they drive it off, not through evaporation, but there's another process. I can't honestly remember what it was, but again, that's something that I can find out for you. So that's a benefit, is just eking out the last that you can. One of the drawbacks is anytime you're using a chemical process, you're also going to have a larger investment, not only in the product, but you also might come under other regulations and other separators that are needed. You might be talking machinery, or you might be talking product. As was mentioned before, if you're doing small scale production, it's not really cost feasible. I had worked in a small ag university in the Midwest, and they were probably pressing, well, they had tanks that were probably like 200-gallon tanks, and they were just doing the raw pressing. And it was right above my office. In the summer, we were in an area that had sometimes 98% humidity at 90, 95 degrees. And boy, I tell you, you'll never forget the smell of canola when you have to sit all summer, just having it waft up through your door and up through your windows and such like that. And that was just the raw stuff itself. It wasn't caustic, but it certainly wasn't pretty. And there are then again also with the solvents with disposal. I don't know what the recycling factor is how many times you can run the same solvent through after you've extracted it, how many times you can go ahead and reintroduce it and extract it again before you compromise the integrity of the chemical. And then if you don't get all of the, so obviously it's very beneficial, the solvent is, to get all the oil out, but then if you don't get all the solvent out, it is tough on the seals. So, as I mentioned before. So, there's just a very, very common press, and that's out of Montana State, and I believe by looking at that may, that may be the camellia, I believe. But this is a very simple engine. Obviously, it's a very small scale. This might be something that that a farmer has in his pole barn to go ahead and produce, you know, just enough to go ahead and run his tractor for whatever duties. So, canola oil, you'd asked about not the recovery, but what the output was, I guess. And it's been estimated, and again, this is from the University of Montana, a state where they have quite a bit of experience. If you had 100 acres of canola, you can end up with basically about 55 tons of material. And so they figure that by the time in weight now, except for the gallons, and I'm not sure how many pounds to a gallon of oil, but you'll get about 4,200 gallons of oil, and then you'll get 36 tons of meal. And that's assuming that you've gotten 75% out of it. So this is a situation where you've got a really good press, but you're probably not using solvents, so you're certainly not using them thoroughly. The benefit sometimes of having a small scale, though, is if you have a cattle or a hog operation, you can go ahead and figure out, I won't be able to use as much in the tractor, but the oil helps to put weight on the animals. All right, you have a much more supple meal that you're giving them, not as dry. And oil, of course, has calories also besides BTUs. So I mentioned that there's a whole industry then that takes separate types of biofuels and will go ahead and mix them to make a product that you can run, you know, your vehicle engines off of, your diesel engines and such. And the advantage of diesel, so with ethanol, a lot of that, which was not an oil base, but was more of kind of a sugar alcohol based system, a lot of that was mixed in then with gasoline. You'd see the E85, some of these standards that would let you know to what degree there had been ethanol as an additive. And the advantage of mixing some of these oils, though, with diesel is that besides transportation, again, you can use these, especially in Alaska where we have a lot of remote communities. If there can be some type of growth of some of these materials, you can go ahead and use them on the gen sets that go ahead and produce electricity. Diesel obviously is kind of the fuel, the currency fuel throughout, especially rural Alaska. So when biodiesels are made, and it's going to depend to some extent on your mixture, obviously. All this is to give you an idea that I think it comes out roughly here at a little less than, let's see, it'd be a little less than, what, 8% maybe. When you do your mixture, it's not going to be the same as what you normally get of pure petrol. Not that there's a degradation of the petrol itself with the mixture, but you're just not getting as much from the actual biofuels. And that's not to say that there aren't enhancers. There are different types of treatments that are used to try to boost performance. But again, in general, it's just not a straight across trade. Well, I went 25% bio oils, and I went ahead and went 75% actually petrol. I should come out with the same amount. Doesn't happen. So this is just kind of an idea of a typical recipe. They'll go ahead and they'll have oil. They'll add in alcohol. They'll add in a catalyst, and I don't know what chemical that catalyst would be, but sodium. Okay, okay, so it'd be a sodium hydroxide. So you've got a little bit of additive, and again, for a place like, for instance, Delta Junction, or if they're growing seeds, which they don't tend to do on Palmer. Palmer tends to be more vegetables, and other product that is for, you know, produce consumption, not so much grains. But if anyone was serious about getting into the industry, they would obviously need to have chemists on hand, and you need to have machinery that measures, calibrates very carefully what your mixtures are. Now, one thing that I'll mention at this point, only because we're going to talk a little bit about gasification later, is that an interesting development that's happened in Delta Junction is that they are growing crops for BTUs to burn for fuel. But it's not necessarily to make biofuels or bioliquids, let's put it that way. All right. What they're doing is they're attempting to grow, right now they're at 5,000 acres, which isn't a whole lot of barley, that they've just been kind of getting by on to produce for a little bit of the livestock needs that are in the state. And that's been going down, the amount of livestock in the state. In fact, Department of Agriculture's standard figure is that 5% of all the food consumed in Alaska comes from Alaska. 95% is coming out. And that's actually a pretty liberal figure. I've heard as low as 2%. Okay, so those kinds of industries we had, you know, we had MAP made for dairies. MAP made went down the tubes. Northern Lights is still hanging in there, so they use some of the meal for barley, which is a crop that grows real well with canola up in Delta Junction. But, you know, I don't know how long, you know, those processes are going to hang in there, so to speak. And so what a lot of the farmers would like to do is they'd like to take the military base, which is the Star Wars Missile Interceptor Base, Fort Greely, and they would like to sell them barley to burn in new furnaces, and then to go ahead and distribute the heat from that throughout the entire base. And they would actually be converting, believe it or not, they would be converting the heat because of the minus 50, minus 60 below winters. The best transfer mechanism would be steam. So they'd be, if the farmers had their way, they'd be burning steam. I mean, be burning biomass, and the fire from the boiler would be evaporating water into steam and driving turbines that would then, throughout the base, go ahead and supply not only steam, not only heat, but there has been some talk, though the main entity that takes care of the utilities is not interested in this, of even having turbines that would, different cell turbines off the steam that would produce electricity and try to make it self-sufficient. The Army has mandates not only for using biofuels that are a certain percentage green by a certain year for its jets and its ships, but it also, in 2008, the entire military system was given this mandate to go ahead and to be green with the utilities on their bases. So we'll see how that works out. Right now, the lumber folks are given a run for their money because state forestry is sitting on so much wood that's dead on the ground or standing up dead that they would like to liquidate. But a lot of the lumber men up there would, of course, rather use wood than the barley. But that's just a side note of a product that's a crop product that has a decrease in demand because the livestock is going down. It's not oil, so you can't press it for fluid. Okay, it's not an oil seed. And the main use, of course, for barley is what? Yeah, and the problem is that you have an isolated island that they could produce good barley, but by the time you figure the transportation costs of sending it, I mean, there's some microbreweries in Anchorage and Juneau, right? But by the time you consider in large quantities sending it down to the lower 48, it's not even cost effective anymore just because of the transportation costs. So they're sticking with barley because growth-wise it makes the most sense in a very short season with a lot of sunlight as far as just its nature on how it grows. So anyway, that's just an energy illustration that doesn't have anything to do with biofuels, but it's kind of interesting to see how it's playing out. So when you make these mixtures, then you're getting 10 or 20% as a glycerin. And here, in a micro scale production, you're talking about maybe making 300 gallons or less. So this would be something possible that if farmers wanted to make biodiesels, okay, for other applications, maybe generator sets and stuff like that, that may not be as conducive to using raw canola, such as a regular tractor engine. There is the ability to go ahead and have individual farmers actually produce the biodiesel. So for that, we figured earlier the amount of canola that would come off of the acreage. Here they just show you the difference in scale. You could get really small producers and come out, but you have to do a whole lot of batches or larger, depending on what you think your usage is going to be. The main thing, though, that I think to take away from this is that I don't think that biodiesel in general is a very stable way of investing time, effort, and new machinery to use your oil seed, and here's why. According to this, if your seed costs change just at 1 cent a pound, because of the process, it can make the difference of 27 cents a gallon, a quarter a gallon of your output. Okay? If your meal revenue changes, it really isn't all that volatile, nor your crushing. But again, just the point being, not trying to equate all these numbers to different parts of the process, just the point being that, you know, from year to year, seed prices can vary. Well, corn started out last summer, I believe, at around $2–3 a bushel, and at some points in the season, it was bouncing up towards $8 a bushel, $7–8 a bushel. Well, that's a huge variation for the seed product, whether you're going to use it for planting seed next year, or whether it's your end product. Here, you know, it just seems to be fairly volatile. Well, maybe not. That's not a right word to use in a chemistry process, but seems to be not so stable. Let's put it that way. So this just illustrates that over the last half decade, that we've gotten quite an export market going, and this again is U.S. production, mostly peaking out in 2008. 2008, as I recall, I mean, that's when we had our financial crisis on Wall Street, but also the markets were going bonkers as far as ag product. And so obviously, along with more exports, you had more production. Now, I think the interesting thing here is just to see that you have fuels that just over the course of a decade, well, almost a decade, 9 years, you have biodiesel prices that are intermingling with diesel prices, but especially with this B100, and you're talking again at an aggregate level for the whole United States, they tend to be keeping pretty close together and in step. And remember that probably isn't unusual, because your costs in producing seed or product, ag product, is highly dependent upon the cost of petrol because most of your machinery relies on it. So this isn't unusual to see this. Now, probably more practical for the coastal regions of Alaska is to talk about what to do about biowaste, not from plants so much, is from fish or wood. So this is an open source unit, which means this. The guys down in Berkeley, all right, who made this thing want the world to know about it. And so you can go to their website and they'll sell you one of these, and I'll explain it in a minute. Or you can download the CAD drawings and the descriptions of how to make the thing if you wanna. All right. So if you got creative people, this could be a cheap way of getting electricity. Now I'm going to talk about a couple different processes here when talking about fish wastes and what they can be used for. But probably one of the ones that we have the most data on that's been experimented out of Palmer is gasification. And that simply means this, that you're taking any type of organic matter. It can be corn cobs that the corn has been stripped off. It can be grasses like switchgrass or willow brush. It can be turkey poop, such as they do in the Midwest on big turkey farms. It can just be regular old hog fuel that's been chipped up from running any type of tree through it, or it may even be sawdust. All right, but anything that's got BTU value, you can run into a drum or a hopper. That's just a 55-gallon drum, okay? And you can go ahead then and create a fire in a chamber. This is a stainless steel, I believe, gasification chamber, where you get a process where you get that tank firing off so hot that when the product goes in there, you can kind of control it. You can keep it on low, so to speak, and you can burn whatever product is in there and then kind of stop the process and get charcoal. Okay? Or you can put the product in and let it burn and come up with biochar, which means that all the BTUs have dropped out of it and it kind of crumbles. It's just like black. It's not ash, but it's kind of like really, really soft charcoal. Okay? And the advantage to that is that it's used often in fields or in gardens because it's a retainer in which when you put organic matter, whether it be fish guts or whether it be fertilizer, it kind of holds it and it's kind of like a time release capsule. Okay? Or you can put the organic matter in and just let that baby burn up until all the gases have totally fried and you have nothing but just a little bit of ash. All right? So, when you burn up those gases, you basically are vaporizing the product because of the incredible high temperatures. You're vaporizing your corn cobs or your chips to the point that now you've got these gases that have been burned up and they're being ported over on the back side of this to a Chevy engine, a GM engine, a 4-cylinder engine. And it's acting much like gasoline that gets vaporized in a cylinder. Those hot gasified vapors are driving those pistons. And those pistons are running a car alternator. And the car alternator is making current, DC, 12-volt current, all right? And you've got a big radiator on the back of this thing to cool it off. And so you're basically taking any type of organic matter and you're basically having a regular car engine produce electricity. And this will produce 10 kW that'll probably take care of any of your houses. All right? Now, the question always is how am I going to get my 15-year-old to constantly shovel stuff in, right? The feeding mechanism is a whole different deal, and there are conveyor belts and there are bins. But my point is this, is that when you can gasify organic material, all right, you could do 3 things. You could go ahead and burn those gases and pour them off through flue ducting, and you could heat and have space heating. You could go ahead and produce electricity by running it through the engine and the alternator. Or another option is you could take those gases that have totally vaporized all the product in there, and I'm being very, very simplistic, okay? So if anyone's a mechanic here, they'll probably skewer me before I get out of the door. But you can go ahead and port those gases off into another chamber, and you can cool the chamber down, and it will condense into fluid, all right? Now, I don't know to what degree, if you run just wood chips in there and you decide to do that, that you'd end up with necessarily grain alcohol. But I've had somebody tell me before, oh yeah, you know, my uncle used to do that all the time when he was bootlegging right out in the village. I mean, it's a similar process that his uncle used. So this is a unit that these guys from Berkeley, they sell. It's on wheels. You can get the 10K to take care of your house for like 18 grand. You can get the 20K, which is twice as big, for about 25 grand. And you can even get a connex that they stick it into. So think about this for bush application, for a tribal hall, or a small processing facility, or a school that's maybe 60,000 square foot, or a factory. You can go ahead and take 100 kW1 and they put them in connexes. And you have to have a good feeding system, but you can then pull, you can adapt it for heat if you want. Although this one, because of the way it's built so compactly, you just want to use it for electricity. So this gasification method has a lot of different outputs that you can run off it. So Andrew Soria out of Palmer worked with a couple of other researchers, and they said, so by the way, just the generic name of this is GEC, Gasification Experimental Kit. That's like saying radio control helicopter, okay? And then these guys have taken it and they've just incorporated that description of what kind of machinery it is into their name, and you can go on their website and see what they've got going. Well, Andrew Soria had gotten a hold of one of the first GECs that this company had ever put out, all right? And he decided to take fish guts, and he decided to throw them into a blender and mix them with chipped alder sawdust, all right? And then he was going to go ahead and pour the beaker or the blender, whatever, into forms of pucks about this big, and then he was going to go ahead and dry them out. And then once they were dry, they were basically fuel pellets that he was going to experiment with to see what is the optimum burn. In alder and other wood, you have lignits in there. Okay, you have pieces of fiber, right? And it's not just about the BTU value, but there are other mechanics, the form and the shape of the material and such, that can dictate the release of energy, more or less. And I'm being very vague about that. But what they decided to do was they would go ahead and pour these little cakes by mixing in different amounts of salmon. You got 100% of product. And what they found is when they burned different amounts, they first of all wanted to control and drive out all the moisture ahead of time, no matter what amount of alder to what percentage of alder, what percentage of salmon. And they were using salmon heads, okay? And they wanted to go ahead and drive off the moisture. Any idea why? I mean, have you ever burned greenwood compared to dry wood? Smoke, and that smoke happens to be accompanying a lot of gases that are accompanying, you know, I mean, you're losing a lot of your BTUs. You're also within the wood, and this is probably a poor way of saying it, but within the wood, the heat, the fire, the burning of BTUs is having to go ahead and kind of dry the wood out as it burns the wood. And so you get a lot more heat from wood that's dry. And in the interior, we try to get people, not only because of particulate matter that ruins people's respiratory situations if they have asthma and stuff, we try to get them to burn dry, hot, and fast. And by dry, we mean ideally it'd be nice to have your moisture level down to like 20% would be pretty nice. All right? So they have these little probes that they stab in the wood that have little digital readouts, you know. And again, you're going to, the drier it is, by just whatever means you use to drive that water off ahead of time, then your BTUs can concentrate more on getting a hotter fire. So what he did here is he said, we want the pucks that we make after we've poured this slurry, we want it to only have 22%, to be just a little under a quarter as far, well, I shouldn't say, put it that way, to have at least 22% or less moisture, okay? So then he takes these pucks and he loads them into the gasification chamber, and he fires it up. But he doesn't just kind of like you would, maybe starting a fire, put a little bit of paper and then put the log on when you got a little bit of flame. Part of the process, and he's an expert in how you use these gasifiers to get the most bang out of them, he goes ahead and he fires it up with wood charcoal, and it's circulating the gases and reburning them and reburning them and reburning them to the point where he wants to get it up to 1,000 degrees. Okay, I guess you could say he's priming it, so to speak. And then when he's going to add the pucks, he backed it off to 800 degrees. All right, and I don't know if that's due to the preparation of the metal or just the environment, but apparently when he dropped it, he got the best burn no matter what the combination was. And when he figured out the combination, he actually figured out that if you go with 21% salmon and 79% alder sawdust in your slurry, you will get the optimal burn. And for some reason, if you go stronger on the salmon heads and go 28%, all right, and then go 72% on your alder, for some reason the heat they got out, it just dropped. Okay, I mean, if you've ever seen a curve that shows, as you add more of this, there's an increase, in BTUs or temperature. It was like you got to this 21 and all of a sudden just shoom. For some reason, and I don't know the reason why, it just dropped out. And that's not unusual, though, and only particular to this situation. There's some processes that they use when they char wood. They'll do something called torrefaction sometimes. They'll run wood through kind of a gasifier on a conveyor belt, and they'll singe it. And they drive the gases off, and they recapture them in a big chamber, and then bring them back up to heat and continue the wood on down this assembly line. And they get it to a certain point, and they have this all figured out with different monitors and detection devices that are computerized. And they know that they have now charred it or singed it to the point that if they go any farther, a lot of the BTUs are just going to drop out of the wood. And the reason why they do it in this case is because they want to drive off as much moisture up to that point where you might lose your BTUs, okay? Because it costs less to go ahead and ship something that doesn't have water in it, right? But in addition, this product, having the BTUs, is comparable to coal. And so in countries such as in Europe and such, where they're having difficulties because they have real stringent regulations that we don't have on CO2 emissions and such, they'll go ahead and crush it, almost like charcoal, and burn that wood with coal, so that if they're just a little bit over the benchmark that they're supposed to be as far as their CO2 levels, that wood is considered to be carbon neutral. Wood, even though you burn it in the realm of the politics of CO2, because a new tree will probably grow or be planted in its place, it's considered to kind of take back whatever it put off when it burned, so to speak. And so anyway, I bet I can just go like this. I bet I can't. Oh, here it is. So anyway, again, you have engineers who are really controlling these processes because they know if it's just a couple more minutes, you're going to lose everything. So anyway, one of the things that came out of this is that you could obviously gasify then a combination of alder and fish at that particular level, and you could run one of these engines and you could get electricity off of it, heat or some type of other oil. It's a pretty unique study that he did, and Andrew doesn't publish something until he knows that it's been tried and tried and tried. Now, the last thing that I'd like to speak about is using biological waste for combined heat and power. Now, the unit I showed you for electricity, that was kind of more of a personal use, right, for your house, or maybe a small village school, but pretty small scale, right? Maybe up to 60,000, like I said, on the 100K, you could still get a factory, all right? in somewhat Arctic temperatures. But when you're talking about a whole community, often what you want to figure out is how can we go ahead and use organic matter and basically get both heat and electricity. And so you have powerhouses that try to find an optimum point in which the machinery will go ahead and take care of electrical needs and take care of the heating needs. And so CHP, the common term, in general, when you're talking very large scale and you're talking large gen sets, large powerhouses, in general, it seems as though if you can balance out your production system so that you can get 40% electricity and 60% heat, that tends to be a good goal, a good rate. Now let me give you an example. The Tok School was paying a whole lot of money for fuel oil there at 80,000 square foot, all right? And they decided that because they almost burned up in 2004 that they were going to back all the trees off the spruce away from the school. Well, when they did that, forestry said, hey, we don't know what to do with all these trees that we've just lopped off to give a defensible space. So Tok said, well, couldn't we go ahead and, since this was also the time that fuel oil really climbed up, couldn't we go ahead and use that wood to basically go back to the old style system of large boilers just to produce all the heat for the school? And so they figured out, they got a Messerschmitts and some, which is the fellow who works with it is out of Michigan, got some parts out of Austria and such, and they put together this large boiler, and the amount of money that they saved allowed them to go ahead and keep their early childhood program and have a couple extra teachers and such like that just in one season because of the increase in fuel oil. Even considering the amount of capital that they had to invest in. Now they got help from Alaska Energy Authority as well as the legislature for that, okay? But when they got to that point, they said, okay, we've taken care of our heat, but our electricity, even though they're on the road system, is 63 cents or 65 cents a kilowatt hour, which is just about double or triple than what you pay here, I think. I think you guys are right around a quarter, 23 cents or a quarter. Okay, so maybe double. Maybe double of what you guys have here rather than a third. So what they decided to do was, you're producing all this heat from burning all this wood, you're just putting it through flue ducting straight into the school, that's fine. But can we part off some of that heat to evaporate water that will then go through a high pressurized system to turn a turbine that in turn will give us electricity? And they're the second school district in the nation to do it. One in Montana did it, and now they've done it. All right? Steam is kind of a goosey thing to work with. It takes a lot of tweaking and such as that. And they've probably got it up to 50%, as where the boiler works just like clockwork, heating the whole school. Now you've got this steam turbine. Okay? The problem sometimes with the turbines is you may go ahead and set from the get-go your controls to go ahead and pour it off 60% to go into the ducting, 40% to the steam turbine. The problem is that when you take that out of your original source of your burner for heat, that 40%, you go ahead and you obviously convert through the turbine those BTUs into electricity, but the steam turbine, at least in Tok, gave off so much extra heat off the turbine itself, and they didn't have a heat recovery system at the time, but they're looking into one now, a way that you can capture the heat that comes off the actual metal of the turbine and all of this, that they had to put radiators in because the steam would drive the heat up so high it would be dangerous. So they have these huge radiators, and at 50 below, they're boring huge holes through the pole barn of the powerhouse because you've got your original heat, you've got your electricity, but that process also creates heat, waste heat. So engineers try to do this dance. So I just want to point out that you know, an internal combustion engine is what that one gasifier uses. Common, you use it in your cars. Bernie Carl at Chena Hot Springs is using water out of the ground at 140 degrees using Rankine cycle, which is good for what we call kind of a low temperature heat, low production. And then Stirling engines have been used in a Brayton cycle. But the other thing that I want to talk about, and I'll end on, is that if you have waste like fish waste on a large scale, all right, and you don't want to go through the trouble of trying to set up a large process to go ahead and mix it with alder and use it in gasification and such as this, there is another process that farmers use with cow dung that can be used by large processors with fish waste, and that's anaerobic digesters. And what they're basically doing is they're making a sewage treatment plant. They're setting up a system, and there's some that are fairly small. They're setting up a system where you take all your waste, your fish waste, and you throw it, and you basically let it rot without oxygen. And it gives off methane gas. And then the methane gas, which is in vapor form, you have that drive a turbine by firing off, much like that gasifier. You just kind of leach it off of the huge tank that you have your slurry of waste in. And this is also somewhat similar to the process that they even use in landfills. Now in landfills, you have organic waste. You don't know what's in there, right? But you also have stuff like cardboard and paper and like rotten banana peels and stuff like this. And so now they're drilling wells down into landfills to capture methane that naturally is being created as the landfill has covered ever so much there's no oxygen underneath. And you've got this process going on. So it's not unusual for other types of solid waste plants to be built to take advantage of this. But again, it's something that this is not specific to a fish cannery, okay? But it gives you the idea that you have some type of containment vessel, you have some type of inlet of your wastes, you've got some type of mixing, you end up with some solids that go out to a lagoon, or you could also use as fertilizer or compost, all right? And then you're actually bringing your gas out and you're flaring it off or burning it in a gasifier or maybe straight to a combustion engine. So let me ask you, we've gone, an hour, about an hour or so, hour, 5 minutes. Are there any methods that you're familiar with that people either here or other communities you've lived in are innovatively taking either growth plant product, whether it be intentional like farm product or algae, or taking waste from animal waste, whether it be dung or whether it be animal parts, and are getting energy out of it? Has anyone ever had a creative uncle or or been a part of an industry?
You